Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Aina Akila and I will present about the introduction, which is it has 1.1 is background, 1.2 is problem statement, and 1.3 is objective. And next, I will present about the background of the project, which is we use a graph theory to present the Zeus Coffee delivery network. In the graph, each location is shown as a node, while the route connecting to the location is represented as a weighted edges. These weights may represent the distance, toll charges, or delivery costs. Graph theory is very useful in transformation and logistics because it helps us to analyze many possible route combinations. For this project, Zeus Coffee HQ Glemery acts as a distribution center, while 19 Zeus Coffee outlets in Shah Alam act as a delivery location. And next, I'll present about the problem statement of our project, which is the main problem is that there are many routes between the distribution center and the Zeus Coffee outlets. Because of this, deciding the routes manually can be very difficult and may lead to unnecessary traveling. So, this can increase the traveling distance, fuel and toll costs, and the time needed to complete the deliveries. At the same time, we also need to consider the practical limitation, such as the physical capacity, outlet demand, and also the number of the lorries available. So, therefore, this project apply the systematic optimization approach to find the delivery routes that are more efficient and suitable for the actual constraint. I will present about the objective of our project. For this project, we have 4 main objectives. For the first one, we represent the distribution network by using a 20 by 20 distance agency matrix. And next, we consider the practical constraint, which is the physical capacity, fuel cost, and the numbers of the lorries. And after that, we apply the capacitated physical routine problem, or we say CVRP, by using a Google OR tools. And lastly, we determine the optimized delivery routes that can reduce the total distance and delivery costs without exceeding the capacity of each vehicle.
Now, we move on to Chapter 2, the methodology of the study. This chapter will explain the step-by-step approaches that we use to solve the Zeus Coffee's delivery route planning. Our methodology follows 7 main stages, as shown in the flowchart provided. It starts with the data collection. From the data collected, we will construct 2 adjacency matrices, in which the first one is for the distance, and then the second one is for the toll cost. And then consequently, the data collected are used to build a network graph. From there, we develop the CVRP model that are implemented using the Google OR tools, and then run the optimization to generate routes, and finally analyze and also visualizing the network graph of optimized route. Each stage is crucial for the next one, as analyzing the final routes that are optimized really depends on getting the earlier data collection and modeling the steps right. The first step is data collection. We focus on the Shah Alam area because it has a good concentration of Zeus Coffee outlets. So the selected areas consist of 20 locations in total, with 1 distribution center at HQ Glemery and other 19 branch outlets, as figure 2.1 suggested. For each location, we gathered 4 types of data as the primary input: the physical location taken from Google Maps, the driving distance and toll charges between every pair of locations, from one node to the next or adjacent nodes, and then the estimated inventory demand for each outlet. And the fourth one is the operational parameters like number of vehicles, vehicle capacity, fuel price, and fuel efficiency. Here, table 2.2 presents the list of all locations with its level, the outlet category such as whether it's residential, business, or office, and the demand in kilograms. Next, for the second step of constructing adjacency matrix, we organize the distance and toll data into 2 separate 20 by 20 adjacency matrices. Rows and columns will both represent our 20 locations, node 0 being the depot and nodes 1 to 19 being the outlets. Using those 2 matrices, we build an undirected and weighted graph. Every node connects to every other node, forming what's called a complete graph, in which every pair of distinct vertices is connected by a unique edge. So in principle, any outlet can be reached directly from the other node. With the graph in place, we formulated the actual optimization problem. But now, why exactly we use CVRP instead of the basic VRP? The basic VRP is about finding good routes for vehicles to deliver to a set of customers, but it doesn't consider one important thing. What? The vehicle's limited carrying capacity. And that's why we have chosen to use the capacitated VRP instead. CVRP is simply an extension of VRP that adds a capacity constraint in which each vehicle can only carry so much before it has to return to the depot. We implemented this model in Python using the Google OR tools, an open source optimization framework that provides algorithms for solving various optimization problems, including vehicle routing, flow, graph, linear programming, and constraint programming problems. Hence, in this study, OR tools is utilized to solve the CVRP model by determining the optimal allocation of outlets to vehicles and the sequence of delivery routes. After the CVRP model was implemented in Google OR tools, it's time for optimization and route generation. The solver refines the initial routes by reshuffling which outlets go to which vehicle and in what order to find a lower cost solution. At the end, it returns the best set of 4 routes it found, along with all 4 vehicles' total load and total cost. Finally, we take those optimized routes and map them back onto our original network, giving each vehicle a different color so the 4 delivery paths are easy to distinguish. Then we check all the constraints held, every outlet visited once, every route starting and ending at the depot, and no vehicle exceeding capacity. So, this is where we move from the raw optimization output to a practical verifiable delivery plan. In Chapter 3, we'll walk through the actual results this methodology produced.
To the solution discussion section. So this section is divided into 5 subsections. So I will begin with the operational parameters, followed by the distance and tool adjacency matrices, network graph, and finally optimization result using OR tools. Okay, I will begin by introducing the operational parameters used in our route optimization model. So as shown in table 3.1, our delivery network consists of 20 nodes, including 1 source coffee headquarters and 19 selected outlets in Shah Alam. So we use 4 delivery vehicles, each with a carrying capacity of 2,000 kilograms. So the model also consider a fuel price of RM 3.97 per liter and a fuel efficiency of 8 kilometers per liter. Okay, next is the distance adjacency matrix. So this matrix shows the traveling distance between the Zeus Coffee headquarters and all selected outlets, as well as the distance between each 2 outlets. So each row and columns represent a location, while each value indicates the distance in kilometers between 2 locations. So we assume the matrix is symmetric, meaning the distance from location A to location B is equal to the distance from the location B to location A. Okay, next is the toll adjacency matrix. Similar to the distance adjacency matrix, but here each value indicates the toll charge in a ringgit Malaysia between every 2 locations. So we also consider the same assumption here, which is the matrix is symmetric, meaning the toll cost from location A to location B is equal to the toll cost from location B to location A. So these toll values are then used together with the distance matrix in OR tools to generate the most efficient delivery routes with the lowest overall delivery cost. Now let's take a look on our network graph, which provide a visual representation of the Zeus Coffee distribution network. So each node here represent either the headquarters or one of the selected outlets, while each edge represent a possible travel path between 2 locations, and the values shown on the edges represent the traveling distances obtained from the distance adjacency matrix. This is modeled as a complete graph, meaning every location is directly connected to every other location, allowing OR tools to evaluate all possible route combinations. Okay, now I will present our optimization results. So as we can see on the left side here, the network graph illustrates the optimized delivery routes, where each node represents a Zeus Coffee outlet, while node 0 represents the distribution center. And then the different color lines indicate the routes assigned to each of the 4 vehicle. Okay, as shown in the graph, every vehicle will start and ends its journey at the same point, which is the distribution center, ensuring a complete delivery cycle. The 19 outlets are distributed among the 4 vehicles so that the total demand assigned to each vehicle does not exceed its maximum carrying capacity. Okay. Instead of manually evaluating a numerous possible delivery route sequence, Google OR tools will automatically identify the most efficient routes while satisfying the vehicle capacity constraint defined in this model. Okay, moving to the table on the right side, it summarizes the optimized routing result for each vehicle. It presents the delivery sequence, total inventory load, and transportation cost for every vehicle. From the result, all 19 customer outlets were successfully allocated among the 4 vehicles with a total inventory demand of 7,670 kilograms. The load carried by each vehicle is below the maximum capacity limit of 2,000 kilograms. In terms of transportation cost, vehicle 2 required the lowest cost with 90 ringgit and 71 cent, while the total transportation cost for all 4 vehicles is 82 ringgit and 75 cent. So overall, this result demonstrate that the CVRP model solved using Google or Auto successfully generate feasible and efficient delivery routes by considering both customer demand and vehicle capacity constraint.
This project successfully applied the graph theory and the CVRP to improve the delivery planning for Zeus Coffee outlets in Shah Alam. The distribution network involved of 20 locations, consists of Zeus Coffee HQ Gallery act as a distribution center and 19 selected outlets. 4 vehicle delivery were used, with each of vehicle have a maximum capacity of 2,000 kg. The total inventory demand of 7,670 kg was successfully divided among the 4 vehicles without exceeding their capacity. By using the Google OR tools, optimized delivery routes were generated with a total estimated cost of 82 ringgit and 75 cents. Therefore, all of the objectives for this project were achieved. Overall, this study shows that the graph theory and optimization tools can help to produce a more systematic delivery plan, reduce the unnecessary traveling, and also manage the physical capacity effectively. And that's all from us. Thank you. Conclusion.